We are going to talk about what independence is and use the multiplication rule. So, two events, E and F, are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Two events are dependent if the occurrence of event E in a probability experiment affects the probability of event F. So here in example 1, is it independent or not? Suppose you draw a card from a standard 52 card deck of cards and then you roll a die. The events draw a heart and roll an even number are independent because the results of choosing a card does not impact the results of the die toss. Okay, so if we draw a heart, that's not going to affect whether we roll a 2. Part B and C are similar, but there's something that sets them apart. So part B, suppose two 40-year-old women who live in the U.S. are randomly selected. The events woman 1 survives the year and woman 2 survives the year are independent, and I'll talk about why. And part C, two 40-year-old women live in the same apartment complex. The events woman 1 survives this year and woman 2 survives this year are dependent. Okay, so what makes part B truly independent here is that they are randomly selected. Okay, so there will most likely not be any relation among the two women that are chosen because they are randomly selected from the United States. Whereas in part C, the two women are in the same apartment complex, so they are not randomly selected. Okay, so there could be several factors that go into play here. You think, if they're living in the same apartment complex, they could be in the same car accident, so whether the first one survives could impact whether the second one does, or if there's an apartment fire. There's just a lot of factors that could come into play because they're living in the same apartment complex and not being randomly selected like they are in part B. So previously we talked about disjoint or mutually exclusive events. That is not the same thing as independent events. So recall that two events are disjoint if they have no outcomes in common. So that is if knowing that one of the events occurs, we know the other event did not. So independence means that one event occurring does not affect the probability of the other. Therefore, knowing two events are disjoint means that the events are actually not independent. Okay, so really that's to say that two disjoint events are dependent. All right, and if I think of an example of rolling a 6-sided die, let's let E be the event that we roll an even number. So that would be 2, 4, 6. Let F be the event we roll an odd number. That would be 1, 3, or 5. All right, that means that E intersect F is the empty set, which means they're mutually exclusive or disjoint. All right, so we know that the probability of E happening is 3 out of 6, which is 1/2, and the probability of F happening is 3 out of 6, which is also 1/2. Okay, but say we are told a roll will be even. Then that means the probability of E happening is 100% or 1, and the probability of F happening would be 0% or 0. So the knowledge of event E would change the likelihood of observing event F. So if we know that we roll an even number, that means we know that there's 0 chance that we rolled an odd number. Okay, so that would make E and F dependent. Okay? So, disjoint or mutually exclusive is not the same as being independent. All right, and in fact, if they are mutually exclusive, then that means they're dependent. All right, so use the multiplication rule for independent events. So the multiplication rule for independent events is the probability of E and F is you take the probability of E times the probability of F. So remember, notation with this would be probability of E intersect F is equal to the probability of E times the probability of F. And this is if they are independent. Okay? So, example 2, probability a randomly selected female aged 60 years and older will survive the year is 0.992 according to the National Vital Statistics Report. What is the probability that 2 randomly selected 60-year-old females will survive the year? Okay, well, they're randomly selected. So they are independent. So we are finding the probability that the first survives and that the second survives. Since they're independent, we're going to take the probability that the first survives times the probability that the second survives. Well, the probability that a randomly selected woman survives is 0.992. So we're taking 0.992 times 0.992, and that is equal to 0.984064. So we'll say approximately 98.41%. Example 3. A manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it's purchased. If there is a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim? Okay, well, here, if they're going to make a valid warranty claim, that means that the equipment is defective and they used it in the first year. So we are finding the probability that the equipment is defective and used in first year. Since those are independent events, we're going to take the probability that it's defective times the probability that it's used in the first year. So the probability it's defective is 0.10 times the probability it's used in the first year is 0.30. You multiply those together, you get 0.03, which would be 3%. So you got about 3% chance that a customer can actually make a valid warranty claim. The multiplication rule holds true if there's more than 2 independent events. So as long as all the events are independent, you can use the multiplication rule. So here we're using the surviving the year example, but now we're looking to see what is the probability that 4 randomly selected. So that means we're finding the probability that the first survives, and the second, and the third, and the fourth. So we're going to take the probability that the first survives times the probability that the second survives times the probability that the third times the probability of the fourth. So the probability for each of those is 0.992. So we do that and we get 0.9684, which would be 96.84%. All right, last thing here is we're going to talk about computing at least probabilities. So we have our surviving example. We want to know what is the probability that at least 1 of 500 So at least 1 of 500 randomly selected 6-year-old females will die during the course of the year. Okay, so the probability that at least 1 of 500 dies. That would mean that for finding the probability that the first person dies, or the second, or the third, or all the way up, or the 500th person dies. All right, these are mutually exclusive events. Okay, they're randomly selected. So because they're mutually exclusive or disjoint, then to find that probability, we can take the probability that the first dies plus the probability that the second dies plus the probability that the third dies plus plus the probability that the 500th dies. Okay, well, that would be a lot to do here. So we've talked previously about using the complement. So think the complement of at least one dies would mean that none of them die. So the complement of at least one dies would mean that none die. Okay, so that would mean to find the probability of the complement, we would take 1 minus the probability of the event happening. So in our situation, the probability that at least one dies would be 1 minus the probability that none die. Okay, so using that idea there, 1 minus the probability that none die, we're going to take, actually let me move this. There we go. So that would mean we're going to take 1 minus the probability that none die, means the first survives and the second survives and the third, and the fourth and the fifth and all the way up to the 500th survives. Okay, well, those are all independent events. So really, we would be taking 1 minus the probability that the first survives times the probability that the second survives times all the way up to the probability that the 500th person survives. Well, we know the probability of a person surviving is 0.992. So we're going to take 1 minus and be 0.992 times 0.992 times all the way up to the 500th person surviving with a probability of 0.992. So we know there's 500, so we're taking 1 minus 0.992 to the 500th power. And if you do that, that's approximately 0.982. So it's about a 98.2% chance that of 500 randomly selected women, at least one of them dies. So to put that just in terms of, so if we randomly select 500 females 60 years old, if we do that 100 different times, then we would expect at least one to die in 98 of our samples. All right. So here is just a summary of the probability rules we have covered so far. The first 2 points come from the first section we've covered. The points 3 and 4 come from the second section, and then this is what we just learned in this section here for independent events.